Hello, welcome to my presentation. My name is Kamil Ridwan Kehinde. I'm a research engineer with Nigerian Building and Road Research Institute in Nigeria. The title of my study is Optimization of Flux Switching Permanent Magnet Motor to Enhance the Traction of an Electric Vehicle. I carried out this collaborative research with Jamilat Kamil at the Department of Electrical and Electronic Engineering at Coventry University, United Kingdom, and Dr. Kyung-sung Wang at the Department of Electrical Electronic Engineering, École de Technologie Montréal, Canada, as an assistant professor. Now let's get into the details of the study.
So for the background of the study, we all know that an electric motor is a transducer that converts electrical energy into mechanical energy by the generation of magnetic field in coils. So as depicted in the picture you are seeing, the electric connection is made up of the traction and the power battery. Optimization of the traction part is the major focus of this study so as to better appreciate the performance of an electric motor. So with the quest of phasing out the use of fossil fuel, cars that run with fossil fuel, and to better appreciate renewable energy, there is need for the introduction of more efficient electric machines, which is the major background of the work that will be carried out in this study. So for the problem statement, we all know the major component of an electric vehicle is the electrical machine that aids the traction of the motor. As we are aware, there are different types of electric motor ranging from the AC induction motor, brushed or brushless DC motor, salient pole, and the permanent magnet motor, which is the focus of this study. A permanent magnet motor, they are actually a synchronous motor that uses rotational permanent magnet instead of field winding, as in the case of induction motor. A lot of studies have shown that they are better at producing rotational torque and power density as compared to many other type. So with the global acceptance of renewable energy, permanent magnet make it easy for them to be used as a power source for electric motor in a better efficient way. So we now have different topology for the permanent magnet motor. We have the rotor permanent magnet and the stator permanent magnet machine. The rotor permanent magnet machine, they have, in their case, the permanent magnets are in this rotor interior. They are arranged in the rotor interior, whereas in the case of stator permanent magnet, they have their permanent magnet placed on the stator teeth. So in this case, it is better than the rotor because that way of arranging them on the stator teeth reduces temperature rise of the motor. So there are now different configurations that have been proposed for the stator permanent magnet, which is the double salient, flux reversal, flux switching, whereas the flux switching is the major focus of this study. So with the numerous benefits of permanent magnet synchronous motor for electric motor, they all have a major general drawback of power region, whereby more power can be generated by the motor. They are usually more noticeable when the motor is running at a higher speed.
Looking at the drawbacks and challenges in various configurations of stator PMs, the main objective of this study in the quest to increase their effectiveness is the design of a new topology for stator permanent magnet motors. So analysis will now be carried out on the proposed model using finite element method. AutoCAD and magnetic infolytica will be used to do the design, which will now be transferred to FEMM 4.2 simulation software where analysis will be carried out. It was then redesigned on Ansys Maxwell where losses analysis and efficiency of the proposed topology will be examined. For the design methodology, as we are aware, a conventional electric motor has a stator part and the rotor part. The stator part, which is always stationary, it is where the permanent magnets are being arranged, whereby the rotor part is the rotational part of the electric motor. As shown in the figure that you are seeing, the proposed topology, the major novelty of this work is the introduction of additional rotor, which is a complementary rotor. So there is an inner rotor, outer rotor, and the stator. So the armature winding which is made of copper is the coils, that are wounded on the stator teeth. So the design parameter used for designing this motor is the design parameter as proposed by Maxwell package for designing a rotational actuator. As seen in the design, the permanent magnet are staggered at 120 degree apart. The winding is done in 3 phases. The winding material is made up of copper. The permanent magnet is neodymium magnet, which is an alloy. The stator and rotor material are M15 steel. Observation was placed on the phase direction of the permanent magnet on the rotor, which will have impact on the output output torque that will be produced. So this is a proposed topology of the 22 rotor 12 stator as designed on magnetic infolitical. After imputing and validating the design parameter on FEMM software, the load flux line distribution was viewed. So the test was carried out on FEMM software. The machine was propelled at 900 revolution per minute speed with a current density of 7 ampere per millimeter square. The current density is the current flowing through the cross-sectional area of the stator winding. So the electromotive flux waveform that you are seeing shown that the winding is done in 3 phases. They came out very balanced with only ripple occurring at the edges of the harmonic on phase 1, phase B, phase A, phase B and phase C of the winding. Why did we propel the machine at 7 ampere per millimeter square? Literature has shown that for industrial application, most naturally cooled machines, the allowable current density ranges from 5 to 10 ampere per millimeter square. So that was why we went for the 7 ampere per millimeter square, which is in between. The curve angle at different angle of rotation of the rotor was also viewed. Looking at the graph you are seeing, the torque when the machine was propelled at 900 revolution per minute ranges between 30 to 30.1 Newton meter, which equals to a torque density of 27.09 kilonewton meter per meter cube. That was gotten because we know torque or power density is a product of speed and torque. So since the speed of rotation is 900 and the output torque is 30.1, dividing it by 1000 to give it in kilo gives us 27.09 kilonewton meter per meter cube. So analyzing the cogging torque. Cogging torque, as we know, is an undesirable element in any electrical machine. So it's usually caused by the interaction between magnet and the stator teeth in any traction machine. As we know, cogging torque usually results in production of noise and vibration of the machine. Cogging torque is usually a function of peak to peak value of the output torque when the machine was run at 900 revolution per minute as we are seeing depicted in the graph. The maximum torque is 1.4 cogging torque while the minimum cogging torque is -1. So the peak to peak value is 1.4 minus 1, which gives us 2.4 Newton meter. So this equals to just 7.9% of the output torque if you remove the cogging torque from the output torque of 30.1 Newton per meter. So with the low cogging torque shows that the addition of complementary rotor to the topology introduce a very low ripple effect and they will experience just little vibration and noise. As we are aware, electric vehicle are not naturally cooled, and with the introduction of modern and advanced cooling system, the current density of an electric motor can go as high as possible. So the simulation was carried out at different values of current density as shown in the graph you are seeing. Interpreting the graph, we can see that the largest output torque, which occurred just below the 80 Newton meter torque output, was when the current density was at 22.5, which also interprets to a torque density of 72 kilonewton per meter cube. This was gotten because if you multiply the speed of rotation, which is 900, by the output torque of 80 Newton meter, dividing it by 1000 gives you a torque density of 72 kilonewton meter per meter cube. So this was the output torque that was experienced just before the motor went into saturation. Discussion about the saturation effect will be interpreted in the subsequent slide. Saturation usually puts a practical limit on the magnetic field achievable by any electrical machine. So the 2D output result presented that you are seeing is for when the machine is running at 7 and at 22.5 ampere per millimeter cube current density. So the more torque that was produced, the more the saturation that occurs. That's why the the flux density distribution at 22.5 is more than when it's at 7. So the simulation result of the saturation point occurred at 1.7 if, as you can see, when running at the rated speed of 900 revolution per minute. This is still acceptable and for conventional electrical steel material.
So now analyzing the losses experienced by the motor on load, it's practically impossible not to experience any losses in an electrical machine. We all know that it is practically impossible. So analyzing the different loss, since we have the inner and outer rotor, so core loss will occur on both the inner and the outer rotor. So examining the losses that were experienced shows that a loss of 130 watts occurred when on the core or iron losses by the inner and outer load, interpreting the graph, whereby the eddy current is negligible, is relatively low, not negligible but relatively low. The eddy current loss is since the alloy material of the motor, of the stator and the rotor is roughly 10% of mid steel. That's what resulted in a low eddy current. So we can further reduce the eddy current loss to the barest minimum in the electric motor by segmenting the magnets when arranging them on the stator when practicalized. So for the efficiency curve, efficiency of the machine, as you can see, is 87.39, which justify the approach of configuring the flux switching permanent magnet motor by introduction of complementary rotor. So you can still further raise the efficiency of the machine by reducing the losses on the iron or core by improving the the packing factor of the machine. So this is the output efficiency of the machine, which is justifiable.
Looking at the electromagnetic performance of the 2212 slot double rotor machine topology proposed, when the motor was running at a rated speed of 900 revolution per minute and current density of 7 ampere per millimeter square, the peak-to-peak cogging torque experience was just 2.42 and the rated output torque was 30.1. The rated output power was 4.37 kilowatts. The rated efficiency was 87.39. Also, the torque density rated was 31.29, while the maximum torque density experience was 72 kilonewton meter per meter cube. So in conclusion, the high efficiency and torque production properties of permanent magnets makes them well suited for traction and propulsion of electric vehicle. So changing the phase direction of the magnet on the stator had an increment impact on the torque that was being produced. So for a maximum torque density of this proposed machine going for as high as 72 kilonewton meter per meter cube with a low cogging torque of 2.4 newton meter and an efficiency of 87.39, the phase direction change of the permanent magnet on the stator slot had a very good impact on the torque, and the introduction of complementary rotor is also a good justifiable approach in designing the flux switching permanent magnet motor. So also on the losses experienced by the motor, the eddy current loss experience is significantly low and can be further reduced by segmenting the magnet into different sections, which will also increase the efficiency of the motor further to as high as like 90%. So conclusively, the flux switching permanent magnet can be easily used on electric cars and with a reduced power consumption and appreciate the introduction of alternative energy to fossil fuels. So they usually use within the range of 75% of their rated power, so which makes them much more better and optimization of their approach the best alternative for electric vehicles. Thank you for listening to my presentation.